Today, we're going to do Chapter 4, which is here. Chapter 4, I've added a couple new projects. We'll try to demonstrate those. Someone asked me to talk more about how to do the one where you crack the one-time pad, the crib drag. So it's best if that person is here either on Twitch or physically, so I can find out exactly what your problem is, but I'm happy to talk about it some more. But let's start with Chapter 4. So, linked lists are a real important data structure, although I have never used them implemented in Python, and I'm far from convinced that's the best way to do it. However, here we are going to talk about how to implement in Python. Now, I use them all the time, but I use them in the form of the heap in the operating system to do heap overflow attacks. Then they're written in C primarily. But anyway, that's the point. So an array is the simplest data structure to store a bunch of data, and probably the fastest if your data is very simple. But then linked lists are the next one. The main advantage of linked lists being you can grow and shrink them at runtime. Arrays you usually define once at the start of a program, and they have fixed size. So arrays are all we had back in the old days of Fortran. You'd have just blocks of data all the same size and just in a row. So you might store something like, this looks like they stored a 1-byte integer. And so you just have a series of bytes, and therefore it's really easy to access it. If you want to access the 100th point, you just take the start and then add 100 times the size and get there. And you can do that with a single machine language instruction with modern processors. It is very fast. So this is the fastest access, random access. You can access them in any order. It's very nice, but the limitation is you have to have, every object has to be the same size, and really usually the same structure. And you have to know how many there are at the time of creation. So this is good for things that you're going to store in memory. Also, if it gets so big that it won't fit in RAM, then you lose a lot of that efficiency, of course, because then you have to go on the hard disk. But anyway, that's an array. Arrays have been around forever. They're very valuable. But lists are more flexible. As I mentioned, this is the main data structure we're using in Python. Usually, if you don't know what to do, use a list. Lists are great. And a linked list it's not just a normal list, it's a list that has data, a pointer to where the data lives. In this case, they're storing a string, and instead of trying to store the string here, they just store a pointer, and then a next pointer. So each item points to the next, and the last one points to none. This is the way heaps are allocated in memory. And the reason they do it this way is so you can dynamically allocate a heap and then dynamically free a heap. So the point of this is your memory is not permanently allocated the way it is for an array. You can grow and shrink this as your program runs, and so you use it for temporary storage of data like large data. So if your program is listening for network traffic, you're going to get a bunch of network data, you're going to have to store it somewhere and process it, and then you're going to have to throw it away to make room for the next batch of network data, and so on. That's what a heap is good for. So like I say, the array is very fast. Storing data is very fast. Traversing it, moving from one to the next is very fast. Accessing data is very fast, order of one. It doesn't matter how big it is or how long it is. The process of taking the base address and just adding a multiplier times the size is very fast, and it doesn't depend on how big that size is. So it's great. The only problem is insert and delete get slow because I don't know why you have to insert, because I guess, well, you know, they say that. Now I'm thinking about it. I don't think I know why an insert or delete would be slow. You could just put it at the end. Oh, I see, you can't put it at the end. It's a fixed size. So you'd have to find a location. I'm a little confused. I guess this would be an operation that changes the size, and I'm not quite sure when you would do that for an array. So I don't think I can explain this statement, although I guess they're thinking, if it was sorted, I can understand that. You'd remove one, and then you'd have to roll the whole thing back. So I guess that's what it means. To delete this one, I have to roll all these back to the left, and that would be scale n. And if I inserted another one here and made it bigger, I'd have to shove all those aside. I guess that's what they're talking about. Normally, you don't do these things to an array during runtime, but if you did, it would be slow. All right, so linked list, insert and delete are very fast because to insert a new item, you just add it at the end. And even if you end up linking it in the middle, you still add it at the end because they don't have to be in order in memory. So inserting is real fast, and to delete one is fine. You delete this one, all you have to do is update this pointer to jump over it. So it doesn't matter where it is or anything. So insert and delete are fast, but store, traverse, and access are slow because the only way to find the 100th element is to start at the first one and hop 100 times because you don't know these pointers and they're not in order, so you can't predict where it is, so that's the problem. It's sort of like magnetic tape. Magnetic tape was fast, and cheap, but the problem is that the data you need is at the other end of the tape. You have to wait while all that tape rolls by, whereas hard drives are much better that way. They can immediately go to what you want. All right, so linked lists are here. Each data item is called a node. The node has data and a pointer. You store your data and you have a pointer to the next one, and the last one points to none. That's how you know the end of the list is there, and that's it. A very simple data structure. These nodes are containing pointers to data as structures. That's one way to do it. And so there's 3 nodes. You have 3 data items, and the last one points to none. So you can implement it here by defining a class that's going to have your node will have a name, and your node.data will be the data, and node.next will be the next pointer, which is none. So you have 2 attributes, self and data, in your node. So for a singly linked list to look like that, you can create it here. You define the class node, then you just declare 3 node objects, specifying the data, and then you can set the next pointer to point to this address, and the next pointer to point to that. This sets the data, and this sets the next pointer. Now you have a list. Now you can traverse the list. You print the current object, N1, and then you go to the next object, and you hop down the list. This is the slow process of traversing. By the way, this is also how you verify the integrity of a list. Cisco routers have a process called check heaps that runs every 30 or 60 seconds that does this. Because heap overflow is a serious security vulnerability for Cisco routers. So to prevent this, they have a process that runs every 30 seconds that traverses the whole heap, and you hop to make sure you end up at the end where you should. And if it fails, it reboots the router, throws away all the packets in processing, and starts over to go with a fresh, clean operating system. And that makes it very secure. The first thing you have to do is somehow find a way to kill that process before you have more than 30 seconds to take over the router. Anyway, all right. So you can improve it. Now, one thing about this system here, this is sort of unprofessional because the end user has to refer to nodes and internal things like node next. And that is considered unprofessional because that's an internal detail of the list that you probably shouldn't have to see from the outside. It would be better to encapsulate it with more meaningful abstractions. So here, you have the node defined elsewhere, and then you create this class called singly linked list that has a head and a size. And then the end user just sees this stuff here. I define a singly linked list, then I just append data to it, and it figures out the pointers and everything without me having to do that manually. So that's friendlier. The one thing to notice is a generator method here ends with yield instead of return. And yield preserves the value of temporary variables when you're calling it again. The details are in your book. I've never used this, but this is cool. Like I say, this is the kind of advanced data structure definition that I'm used to seeing in C++, not in Python, but Python does support it. Python is really very advanced. It has a lot of fancy features that you often don't use. But anyway, there's the code for a live demo, which I don't think I'll do. Let me check the Twitch for comments in case there are any, and there are none. Okay. Anyway, so you can have a list with head and tail pointers. And so now you've got not just a pointer, you have a pointer to the head, you have to have that to get started, and you have a pointer to the tail of the list too, and now append is more efficient. Now you don't have to traverse the whole list to find a spot at the end to add one, you can zip right to the end to add one. So at the expense of making it a little bit bigger and taking a little more time to create the list, you make it faster to do append. So inserting a node goes like this. You put a node somewhere, and it doesn't have to be in this physical location here. It can be anywhere in memory, at least anywhere in the memory segment assigned for the storage of this. And then you just have to change a few pointers. You have to change the previous pointer of this one to go here, and this one goes to the next here. So you lose this connection, and you put this in the middle. So all you do is store it someplace and overwrite a couple of pointers, and now you have added an element in the middle of a list. So if there's no link to the tail, it's going to be order n because you have to traverse the whole list just to find the end where you're going to put it. But if you have a link to the tail, then it's order 1. It doesn't matter how big the link is. You take one step to the end, you add the new thing there, you update a couple pointers here, and they're calling that order 1. Now I might argue about this because how do you find this pointer to update without traversing the list up to that point? I might think it might still be order n in the worst case. But anyway, all right, that's the idea there. And here's the thing that will append at a location that does it, but I think it's easier to understand from the diagram. All right, and you can query a list. Asking the question, is something in a list? And I've talked about this a lot in the projects. You make a list of things, and then you say, is this element in the list? And that can be really slow unless you sort the list and implement a binary search. So to query a list, you're just going to go through the list, hop, hop, hop. Look at the first item, look at the next item, look at the next item. This is going to print them all out. And here, it's going to search for it. And here's the search is just going to hop through it to see if it's in there. Check the first one, check the second one, check the third one, and there's nothing more you can do more efficient than that if the list is not sorted. All right, there's the code you need to demonstrate all that. I'm not going to bother doing it live here. I think all right, so to get the size of a list, one way is to traverse it. Then you get the order of n. You have to hop the whole list to see how big it is, because you have to hop, hop, hop until you hit the none. The alternative, again, would be to just prepare that all along, keep track of the size. Every time you append an item, add one to the size. Every time you delete an item, subtract one from the size. So you could prepare in advance to have the size already stored there. Then, of course, it would not depend on the size of the list at all, how long it takes to determine the size. So deleting the first node. You're going to delete a node, you delete this one, and all you do is move the head pointer to the next one. That's really all you have to do. So now the list starts here instead of starting there. So that's pretty easy. Deleting the last node is similar. You take this pointer and point it to none. So you take your current and previous, you define head, previous, and current. And now that you've defined these, and you may have to traverse the list to find these, previous and current, then you take previous is now the end of the list, change that to none. And there's also an interesting thing here. When you delete something, there are two choices. You can just delete the pointer and leave it hanging around in memory, which is a security risk called memory remnants, which is how almost everything is done in computers. Or you could actually clear that memory, which is generally regarded as a waste of time, and you usually don't bother. And this leads to a whole lot of problems. You can steal data from memory. I did this at DEF CON, or I hope a few years ago. You could steal passwords from browsers in RAM. You can just read the RAM and find passwords it left behind. There is a data structure, a data type that came out in 2004 in Microsoft Visual Studio for ephemeral data that will be erased when you delete it, but most coders just don't bother using it. They use the wrong kind of data structure, so they leave stuff hanging around in memory that is confidential, like passwords. And if you're working on a hard drive, that's retained even when the power's turned off, and the next person gets it when you sell your computer or throw it away. So that's an issue here where you actually want to clear this, but typically you don't worry about that because you're going for performance. You just leave it there, because sooner or later it will get overwritten by new data, and not all data is sensitive. Anyway, you're going to delete a node in the middle. Then first you have to get to the node you're going to delete, so walk the heap until you find the previous and current, and now you delete this one. All you do is change this pointer to jump over it, and now it's gone. And like I say, you may or may not actually bother to erase that data. Jumping over it means it's no longer in the list. All right, and that's the end result. So, pretty simple stuff. By the way, if you want to clear a list, that's extremely easy. Just change the first pointer to none. There, now the whole list is empty. It's probably still sitting there in RAM, but if you access it by the name of that list, you will find nothing, an empty list. So that's easy. I should mention, by the way, this is why you could sell your iPhone. If you have an Android phone, especially a cheap one or an older one, you can't sell it because there is no way to clear the memory of all your personal data. If you have an iPhone, ever since the 3S, you can do this because what iPhones do is they always encrypt all the data right from the start. And when you go into the settings and click Reset to Factory Default, it deletes the key. It doesn't even try to erase any data. It deletes the key. Now all that data is unreadable. This works perfectly well in practice. A forensic company bought 100 used iPhones from eBay and tried to retrieve data from them and were not able to recover any personal data from any of them. So this works. It's like this. Very easy and fast to delete. You just delete the first, use the first pointer, and all that data is no longer accessible. Although, it might still be hanging out in RAM in this case. But anyway, this is, right, then there's doubly linked lists that are a small step forward. Every node now has a next pointer and a previous pointer. So you can walk forward or you can walk back. So it's a simple extension of what you had. So you have two nodes, each one has a next and previous, and this previous points to none, indicating the start, and this next points to none, indicating the end of the list. So you can insert a node at the beginning, and if you do that, you're going to have to find a place to store the node, and then you're going to have to change the head to point to that node. And you're going to have to change this next to point to what used to be the start of the list, and this previous to point here, and that previous to point to none. So it's a little more complicated, but conceptually pretty simple to add an item to the beginning of the list. Inserting one at the end, this used to point to none, so now you just take the forward pointer and point to your new data, send this previous to that data, and put none here. So that's sort of the mirror image of adding it at the start. And you change the tail pointer to point here. And if you insert in the middle, first you traverse the list to find someplace to store it, then you have to update 4 pointers. And as I mentioned, so now you're going to have to this next pointer to point to the new data. The previous pointer here is going to have to point to that previous. The previous pointer, this one, has to point to the new data, and this one has to point there. That's how you insert something in the middle. It's not going to physically be in the middle, contiguously in memory. That would be an array. It's probably at the end, but the pointers are adjusted, so you'll hop through it, and your list is what you might call fragmented in memory, which doesn't matter. And this is deleting a node in the middle. This diagram, I've been using one like this for at least 20 years because this is how you take over a computer with a heap overflow. So think about how you delete this thing in the middle. So you delete a chunk in the middle. Now, this next pointer has to jump over and point to this one. And this previous pointer has to jump over and point to that one. So when you delete this data, it's going to have to change this previous pointer and that next pointer. Now, the reason this is useful to take over a computer is if you have a heap overflow, that's when the data can grow too large. So you're able to write to the data, and you're able to overwrite these next and previous pointers. So if I'm able to overwrite the data here, and then there's a delete operation, I end up updating a pointer, and I can control the address of that pointer, and I can control the data going into that pointer. So the end result is I gain the ability to execute an arbitrary write instruction under my control. And you can easily take over a machine with a write instruction. All you have to do is find some address that will eventually be used and overwrite it with the address to your injected code. So you do this. I'm going to be teaching exploit development next semester. We'll be doing a lot of this hands-on. It's good fun. It's much easier on Linux than Windows. Linux has a nice simple heap structure like this. Windows is very complicated. It has multiple heaps. It has weird connections in the heaps. Heap overflows are painful on Windows. And Microsoft has wised up. And starting about 5 years ago, they have a Blue Hat conference where they pay the best hackers in the world to go to Microsoft for a conference. And they will pay you $100,000 if you find a way to hack into Windows. And they'll pay you another $100,000 if you write the fix that blocks it. So Microsoft's heap defenses have been getting much, much, much better. So they have defenses that watch for anything funny happening with these pointers and block it. So it's getting harder and harder to get in, which is what should happen. Anyway, and then there's circular lists. I mean, it's simple enough to understand. You take the tail and point it back to the head. Now it just goes in a circle. There really is no head and no tail. It's easy enough to understand. I was sort of confused to think, why would you do this? There's some use cases coming at the end. They seem pretty contrived to me. I guess these exist. Obviously, you can do it. You could doubly link it. You could have forward pointers going all the way through and reverse pointers going all the way through. Simple enough to do. But the practical application is not obvious. So singly linked list. If you think mathematically, it's a way to represent a sparse matrix or a polynomial where you have ax squared, ax cubed, bx squared, cx plus d. That turns out to be extremely important. There are a bunch of mathematical problems related to these. In particular, modern cryptography is done this way. If you do lattice-based cryptography or learning with errors, which are what we are all going to have to learn now. These are the post-quantum cryptographic systems that are just being approved by the National Institute of Standards, and they're going to replace the existing systems like RSA. And they use a lot of these polynomials, so you get used to it. And also, like I say, you have a heap in your dynamically allocated memory in the heap is just a singly linked list. A doubly linked list could be a thread schedule to maintain the list of processes, although I don't know why you'd have to have a forward and back pointer. Most recently used and least recently used caches in the OS. There certainly are a ton of these. If you take any modern operating system and point to the bottom and right-click on it, it'll show you recently used items. I don't know why they necessarily store that as a doubly linked list, but according to your book, they do. Undo and redo makes some sense. Because you're doing something, then you want to have like your browser has a back button, so you want to go forward and you want to go back. This makes sense to me, undo and redo, you keep track of everything you've done. I remember in like 1973, I wrote an assembly language program to draw things on the screen, and I had the idea then that at that time memory was very expensive and very small, so you couldn't store a whole image very easily. So what I stored was the steps to draw it, and it would just take the pen and dynamically draw it, and it just stored the motions. It was like the thing that later turned into like SVG, scalar vector graphics, it was like early pre-generative that. But it was pretty cool though. You could undo it. You could draw the thing and you could undraw it. Anyway, so they say it's good for round-robin scheduling. Now this I understand. If you have a round-robin system, one simple one is, in fact, I was just showing this to another class the other day. Let me show it to you here. Okay, if I clear and make this big. Okay, if I want the address for Microsoft, I dig Microsoft.com. Okay, I get 4 addresses. This 133 is on top. If I do it again, 246 is on top, 133 is at the bottom. This is simple round-robin scheduling. What they do is every time someone wants to go to Microsoft, they give them 5 addresses, and then they rotate the order of them. So next person gets them in a different order, and next person gets them in a different order. That load balances. Now you'll get approximately equal number of customers going to each of these addresses. This is a simple way to implement load balancing, and that's a good case for circular list. You rotate the list. All right. And they say undo and redo is here, which I'm pretty skeptical about in Word, because I haven't noticed that if I go undo too many times in Word, I end up back where I started. That is not what happens. And that's what would happen with a circular list. I think it's a doubly linked list, not a circular list. There's an interesting structure, which I Googled to look at, called a Fibonacci heap, which I think is somewhat beyond this course. A pretty interesting structure, and multiplayer games swapping between players. Now that I understand, next player, next player, next player, now the first player. That would be a logical thing to do in a loop. Anyway, those are examples of what they're good for. And I got a few Kahoot questions about them. And there's no new comments here, okay? All right. So let's try the Kahoots, which are here. I think I need to make this a little higher to end up in the stream. All right. Take a quick look at the stream. Yeah, that'll do. Okay. By the way, another example of a circular list is logs. Most logs only log to a certain size, and then they throw away the old stuff to make room for the new stuff. So they're effectively a structure like that loop. This gets a lot of companies hurt. They typically only retain 7 days of logs, so when you get hacked, if you don't notice it before 7 days have passed, you've lost most of the data you need to figure out what happened. That's why your incident response people always try to get you to log more, but your server administrator people always try to get you to log less because it slows things down and fills up your storage units. It's one of those battles. Anyway. All right, maybe we got everybody that's coming. Looks like it. All right, which one of these takes order n to traverse? Yeah, both kinds of lists. You have to hop, because they're not necessarily in any order. So both double and single link lists take order n to traverse. All right. Looks like only one person thought to notice that. Let's see who got it right. It's CC got it right. So, all right. And how about this one? A collection of items stored in contiguous locations. Means right next to each other, right in order. That's an array. Equal, like bricks. Equal size objects just lined right up. All right. So which one gives you random access? Only arrays. An array lets you access every item easily. If you try to look at the 100th item in a list and then the 3rd and then the 200th, you have to run back and forth like a lunatic. It's not random access, it's like a tape. It's very hard to access things out of order. And whereas an array, you can totally access them out of order just as fast as accessing them in order. All right. And which structure is best for dynamically allocated memory? Single linked lists, that's what's actually used. That's what real heaps do. Well, I think some heaps might have, no, I only single linked is all I see, yeah.
What's the doubly?
Doubly linked list just has forward and back pointers, which is nice for implementing something like undo, but you don't normally need it just for dynamic memory. Yep. Yep. I can think it might add something, but it's probably just not worth the bother. Typically, it's a single linked list, a heap. All right. I hope you already know who these people are. If not, put in their names in the canvas or something. Anyway, let me stop this recording.